If the numbers of a number sequence are bounded from the above and from the below by simpler sequences, and if these simpler sequences have the same limit, then also this complicated number sequence has that limit. This is illustrated by this picture shown here. The numbers of the complicated number sequence are the black dots, and they are bounded by the simpler sequences from the above, which are the blue dots, and from the below, which are the red dots. Now the blue dots and the red dots have the same limit. Therefore, these numbers in the complicated sequence, the black dots, must have that limit as well. Hello everybody, I am Mika Seppälä. The Squeeze Theorem, which I just explained briefly, gives us a handle to compute complicated limits. The Squeeze Theorem is a general principle which allows one to compute limits of complicated sequences by comparing them to certain simpler sequences. Assume that a complicated sequence of numbers has an upper bound and a lower bound, which bounds have the same limit. Since the complicated sequence is squeezed between the two sequences which have the same limit, also the complicated sequence must have that limit. Mathematically, this is expressed as the following theorem. If for all values of n, xn is always at most yn, and that is always at most zn, and if the sequences formed by the numbers xn and zn have the same limit capital L, then the sequence yn converges and has also that limit. More briefly, this is expressed as follows. If xn is always at most y-end, and that is always at most z-end, and if the limit as n goes to the infinity of xn equals that of zn, and that limit is some number capital L, then also the sequence formed by the numbers yn converges and limit as n goes to the infinity of yn equals capital L. Graphically, this can be justified as follows. Think of the numbers xn, yn, and zn as functions which are defined for positive integer values of n. Here the horizontal axis is the n-axis, and the dots shown here are the graphs of these functions xn, yn, and zn. Now xn and zn approach the same limit capital L. The dots yn are squeezed between the red and the blue dots. Therefore, as n goes towards the infinity, the dots yn have no option other than to approach this limit capital L. So, thinking of this theorem graphically, this seems almost completely obvious. To prove the Squeeze theorem, starting from the mathematical formal definition of limits, we first take a positive number epsilon. This epsilon can be thought of as being a small positive number, say like 1 over million. It can be arbitrarily small. It suffices that it is positive. And in view of the formal definition of limits, we have to find a number n epsilon, an index, such that whenever n is larger than n epsilon, then the absolute value of yn minus the limit value L is less than epsilon. That is, whenever the index n is larger than this limit n epsilon, then the numbers yn are closer to the limit value L than the distance epsilon. And if we can find such an n epsilon for any positive number epsilon, then we have shown that the sequence yn converges and has the limit capital L. So, how to do this? First, we observe that since the limit of the sequence xn is L, there is a number nx, which of course depends on epsilon, such that whenever n is larger than nx, then the absolute value of xn minus L is less than epsilon. That is, xn is closer than the distance epsilon from the limit value L. This is because we assumed that the limit of the sequence xn is L. This is simply the definition of the limit. Likewise, since the sequence Zn has the limit capital L as well, there is a number nz such that whenever n is larger than nz, then the absolute value of Zn minus L is less than epsilon. Here we have used the definition of the limit for the sequence Zn, and the theorem assumed that the sequence Cn has the limit capital L. Therefore, we can always find such an index nz such that whenever n is larger than nz, then the absolute value of Zn minus L is less than epsilon. As before, this nz depends, of course, also on epsilon. Now we set n epsilon to be the larger one of the numbers nx and nz. Alright, when n epsilon is larger of these two numbers and n is larger than n epsilon, it means that both sequences xn, or both numbers xn and zn, are closer to the limit value than the distance epsilon. That means that they lie on the interval from L minus epsilon to L plus epsilon. So the numbers xn are the lower limits. This is the blue dot on the left, and the zn's are the upper limits. They are the blue dot on the right, and theyn's are squeezed between xn and zn. Sinceyn's are squeezed between xn and zn, and since xn and zn are both closer than the distance epsilon from the limit value capital L, then also yn must be closer than the distance epsilon from the limit value capital L.Yn's are simply between xn's and zn's. And therefore, we conclude that we have found an index n epsilon such that whenever n is larger than n epsilon, then the absolute value of yn minus L, which is certainly less than or equal to the maximum of the two numbers, absolute value of xn minus L and absolute value of zn minus L. Since both of these two numbers are individually less than epsilon, also the larger one of these numbers is less than epsilon, and therefore we conclude that the absolute value of yn minus L is less than epsilon whenever n is larger than n epsilon. This concludes the formal proof stating that the limit of this sequence yn, which gets squeezed between the two sequences xn and zn, is also L, the limit of these bounding sequences xn and zn. As an example of the use of the Squeeze theorem, let us consider the task of computing the limit as n goes to the infinity of n factorial divided by n to the power n. By n factorial we mean the product of numbers all the way up to n, starting with 1. So n factorial is 1 times, 2 times, 3 times, and so forth, all the way times n. Now we observe that for all positive integers n factorial is of course positive, and also n to the power n is always positive. Therefore we conclude that n factorial divided by n to the power n is positive as well, because it is the ratio of two positive numbers. Next we consider the general term n factorial divided by n to the power n. As noted a moment ago, n factorial is 1 times, 2 times, 3 times, and so forth times n, all the way up to n. N is a positive integer, and n to the power n is simply the product of n times with itself. So this n factorial divided by n to the power n can also be viewed as the product of the following numbers: 1 divided by n, 2 divided by n, 3 divided by n, and all the way up to n divided by n. So now we observe that each term, 2 divided by n, 3 divided by n, and so forth, all the way up to n divided by n, is at most 1. Each such term is of the form some positive integer k divided by n, and k here is at most n. Therefore, all these terms have the upper limit 1. And this means that n factorial divided by n to the power n is always at most 1 divided by n. It is, of course, always less than 1 divided by n if n is at least 3. Alright, so now we have observed that for all positive integers n factorial divided by n to the power n is always between 0 and 1 divided by n. The lower limit 0 forms a very simple sequence whose every term is 0. The upper limit is 1 over n, and that sequence has the limit 0 as well. So the lower and the upper limits for the terms n factorial divided by n to the power n have both the limit 0, and therefore we conclude by the Squeeze theorem that n factorial divided by n to the power n approaches 0 as n goes to the infinity. To summarize, now let us recall that the Squeeze theorem is a statement regarding sequences of numbers xn, yn, and zn satisfying xn is at most yn is at most zn for all positive integer values of n. Then if the sequence xn and the sequence zn, if they both converge and have the same limit, then the sequence formed by the numbers yn also converges and has that limit L. Graphically, this can be pictured as viewing the elements of xn, yn, and zn as being the graph of a function defined for positive integer values of n. In this picture, the horizontal axis is the n-axis, and xn, yn, and zn are defined whenever the variable n is an integer. Therefore, the graphs of these functions xn, yn, and zn constitute of a whole lots of dots. Now these red dots form the graph of these numbers xn. The black dots form the graph of the numbers yn, and zn's are the blue dots. Now if the red dots and the blue dots approach the same limit as n grows towards infinity, the black dots yn have no choice but also approach the same limit capital L. Therefore, the Squeeze theorem is almost obvious thinking of it graphically in this way. The Squeeze theorem is a very powerful tool in computing limits of complicated sequences.